Section 3.4 Notes, Function Operations, page 4. This is the final page of the notes. If you have a version that has a page 5 and 6, you can disregard those. You'll see those at other times. Okay. So part 5 here, decompose a composite function into its component functions. This is kind of left up to you and your own devices. This could look very different based on how you write your functions, and that's okay. The best thing to do is try to separate into pieces that are different types of functions. So I have a polynomial function here. Inside, I am going to call that my g of x. So we're going to make g of x 5 minus x squared. And then we'll make f of x the square root part. And keep in mind that's just going to be the square root of x when we compute f of, see if we can color code here for you, g of x. We have got f of 5 minus x squared. And f is that square root of 5 minus x squared. Okay. B asks for f of x equal 4 over 3 minus the square root of 4 plus x squared. Really could do this a couple of different ways. So I am going to write this as, let's see, we're calling this one f of x. So we need an h of g of x. And I could make g of x the whole denominator. So 3 minus the square root of 4 plus x squared. And then h of x would be the 4 over x part, and that whole g would go in. I could also say that my g of x is just this square root of 4 minus x squared part, which then would make h of x 4 over 3 minus x. And we could even go with just calling g of x the 4, sorry, that's 4 plus x squared. G of x is the 4 plus x squared part. And then h of x would be 4 over 3 minus the square root of x. All of those will work. C wants h of x, which is the 1 minus 2x, 1 over 2x minus 3, all raised to the second power. H of x is f of g of x, so g of x has to happen first. That's the very inside part. I'm going to make that 1 over 2x minus 3, and then f of x would be x squared. Okay, so we've got that reciprocal function, or that rational function, on the inside, and then we've got the polynomial, the square, on the outside. Writing composite functions from situations. Sometimes, I mean, this is what we do daily. We've got one intake, I've got my salary, I bring that in, and then I've got a separate function that's deciding how it all gets spent. And so here's the function we are looking at. I'm going to ask you to pause right here and take a minute to read this situation. I am definitely not going to read it for you. Okay, so A wants a function that represents the relationship between the number of wind turbines operating in a wind farm and the amount of energy they generate per day. So my input, I'm going to call N, which is number of wind turbines. My output, maybe I can blow this up so you can see better. There's not a whole lot of space here. I'm going to call E for the amount of energy. Super creative. Amount of kilowatt hours, so energy in kilowatt hours. So here's my function, energy in terms of the number of wind turbines is this 18,400, that's the output of each turbine times however many turbines I have. B wants a function that represents the relationship between the energy expended by an electric car in kilowatt hours and the number of miles. So here, my input is going to be E, which is our kilowatt hours. My output is going to be M, miles driven. So the miles in terms of the energy is 100 divided by 34 times E, the number of kilowatt hours. And just a quick check, 34 kilowatt hours, 34 plugged in for E, those 34s cancel, we get that 100 miles driven. So sometimes you got to kind of play around to figure out how that multiplier factors in here. C wants the function to determine the number of miles that the car could drive based on the number of wind turbines operating. So here's where our composite function comes. I want miles in terms of energy, but I want energy in terms of number of wind turbines, okay? Which is miles in terms of my 18,400 times N. So I get 100 over 34 times 18,400. And you could reduce and leave it as a fraction. I got 920,000 over 17 times N. I'm going to go ahead and convert this just because I'm not writing both because I'm running out of room. 54,117.65 times N. So basically 54,117.65 miles per wind turbine. D, approximate domain and range. So here's our domain. I could really have 0 wind turbines. That doesn't make a whole lot of sense because then we don't really have a wind farm. For the sake of argument, though, we're going to start here with a wind farm with no wind turbines. When I looked up online, it says a large wind turbine is going to have a couple of hundred, a large wind farm will have a couple of hundred wind turbines. So we could go 0 to 200. You could have 0 to 250, 350. Doesn't really matter. Just something that's reasonable. The range there, 0 turbines, is going to take us 0 miles. 200 wind turbines will provide the kilowatt hours for 10,823,529 miles. And I just plugged 200 into the equation above and cranked out miles. We want E, how many miles of driving could be generated daily by 20 wind turbines? So we want M of 20. There's our 20 wind turbines. We've got 54,117.65 times our 20 wind turbines, and we get 1,082,353 miles. Sorry about that.